Okay, good morning, everybody. So I'm going to press on with thin airfoil theory today, and so we'll finish the background material, and before we go to the actual thin airfoil theory, we'll take a short break and talk about project 2. Then we'll go ahead with thin airfoil theory. Any general questions? Are you all looking at that paper for the blog too? Okay. Okay, so lecture 24 today. And in the last class we talked about flow around a circular cylinder, 2D flow, and we talked about how there are multiple solutions depending on the value of the circulation, right? So this is zero circulation, and as you go to higher and higher circulations, you get something like this. And then we talked about Kelvin's Kutajakowski theorem and how this is valid even for bodies that are not circular cylinders. So for example, if you have an airfoil that's producing lift in a moving fluid, you can take integral V dot dl for a contour A, and that will give you a circulation, and that circulation will relate to the lift that the airfoil is generating using Kutajakowski theorem. So that's valid even for bodies like this. And likewise, if you take a contour around some region, and inside that region there is no lift producing object, then the circulation will also be zero. So if you take a contour like this, for example, circulation is zero. Okay, so that's kind of where we stopped. So just like there are no unique solutions for flow around a cylinder, right? So suppose I tell you there is flow going past a cylinder, and the only conditions that have to be satisfied are the infinity boundary condition and the wall boundary condition. Then if you think about it, there are actually infinite number of solutions, because all of these solutions satisfy the wall boundary condition, and all of them satisfy the infinity boundary condition, so they're all valid flows. The only difference is between all these flows is the amount of circulation or the vortex strength that you use to create this circulation. So in some sense, all of these are valid solutions. So to say which one is the correct solution for a particular problem or something, then you have to also specify what is the amount of circulation. Otherwise you can't say which flow is really happening. Most of the time when somebody just gives you some problem like that and doesn't specify anything, that means circulation is zero. But really it could be any circulation. So just like that, there is non-uniqueness of flow solutions even for an airfoil. So that we saw that in page 23-12. And for airfoil here. So we're going to see that now. So for example, if you have a flow past an airfoil, you could have a flow like this. And you could have another flow that looks like this instead. Actually, this will be more like this. So here the flow is going around the trailing edge in this manner, and here it's going in this manner. Or you could have a flow like this. So these are all valid flow solutions. For flow past airfoil. And these solutions satisfy the wall boundary condition and infinity boundary condition. So which one is correct, right? Or in real life, these are all valid solutions, but is there like one correct answer? Some of you know this, right? You have looked at it in other classes, courses earlier. What happens? Kata condition. So which one is correct? Yeah. So what happens is, this is the one that occurs in nature. And we'll talk about this. This is called kata condition. And so these are all, the difference between all of these is the amount of circulation. And it turns out this is the correct circulation. So this is gamma equals gamma correct. This is gamma is much less than, or this is gamma equals 0. Okay, so, or it could be less than the correct value. 0 is one possible number. And here is gamma is too high. So the problem with these two solutions is that in real flow, that means viscous flow, flow around a sharp trailing edge will separate due to high adverse pressure gradient. So notice that even though we are solving inviscid flow, we are bringing this condition which occurs due to viscous effects. It's viscous effects that prevent a real flow from being able to take a turn, 180-degree turn almost around a sharp corner. So we are actually bringing one consideration from viscous flow to actually help us select the correct solution in inviscid flow so that it matches up with what's happening in real life. Okay, so this is called kata condition, and so let's write this out. So among the infinite possible number of flows, at least mathematically, so among the infinite possible flows around an airfoil, so viscosity brings in the requirement that the flow should leave the trailing edge smoothly, and that helps us select the one unique solution among all these infinite solutions. So there are actually two flavors of kata condition for two different shapes of trailing edges. So sharp trailing edge shapes can be broadly of two types. One is a finite angle trailing edge where you have a trailing edge that looks like this. So this angle is finite. And the other is a trailing edge where the upper and lower surfaces meet tangentially. So this angle is 0. Right at the trailing edge, the upper surface and lower surface are tangential. And so this is called a finite angle trailing edge. And this is called a cusped trailing edge. So here upper surface So it turns out that for a finite angle trailing edge, the velocity of the flow comes to 0 at the trailing edge. So velocity on the upper surface equals velocity on the lower surface, and that's both are equal to 0 at the trailing edge. So this is velocity on the lower surface tangential to the, this is at the surface, right? So this is the potential flow velocity at the surface. This is velocity on the lower surface, velocity on the upper surface. And so you can write this as V at the trailing edge equals 0 for finite angle trailing edge. And for a cusp trailing edge, velocity on the upper surface has to be equal to velocity on the lower surface, but it doesn't have to be 0. And so that means velocity at the trailing edge need not be equal to 0. But the upper and lower surfaces have to be of the same velocity, magnitude, at the trailing edge. So this is V lower, this is V upper. Okay, so if you look at the velocity distribution for an airfoil, so usually the type we have been looking at is mostly cusp trailing edge, and for that velocity distribution is usually like this, something like this, right? Velocity on the upper and lower surfaces will meet at the trailing edge, so these two curves will meet, but they won't be equal to 0. But for a finite angle trailing edge, it will look something like this. Okay, so this is upper surface, lower surface, and this is upper surface, lower surface. So this one is a finite angle TE, and this is a cusped. Okay, so mathematically what this means is that kata condition the vorticity at the trailing edge is 0. Okay, so we'll kind of understand this a little better when we go to thin airfoil theory, but let me go ahead and put this here now. The symbol for vortex sheet strength or vorticity is gamma, so gamma at the trailing edge equals 0. So what this means is, you can also think of this as circulation. So let's take a finite angle trailing edge. And let's take a small contour around the trailing edge in a, if you go zoom into the trailing edge, and let's take a small contour like this. Okay, we know for a finite angle trailing edge, velocity is 0. So V equals 0 here, and V equals 0 here. So if you take a contour like this and calculate circulation, circulation will be 0. So gamma at the trailing edge will be 0. So this is a finite angle TE. And on the other hand, a cusp trailing edge is one like this, right? So and here again, if you take a contour right around the trailing edge, and here you have velocity on the upper surface like this, velocity on the lower surface like this, and they are not 0, but they are equal, right? So if you take a line integral, going this way, this will be positive, and going this way, it will be exactly the opposite because it will be negative. So the circulation will become 0. So this is still correct. So gamma at the trailing edge will be 0 for both finite angle trailing edge and a cusp trailing edge. So mathematically, this is the kata condition. Okay, so we have one more thing to talk about, and that's Kelvin's circulation theorem. And that will let us briefly touch into unsteady aerodynamics. So there is a theorem in fluid mechanics called Kelvin's circulation theorem. Without going into how to derive this, we'll just state it and go ahead and use it for our purposes. And this theorem says that for a potential flow, so this says that if you have a certain set of fluid elements, so let's say there is a flow like this, right? So, and at time equals t1, let's take a contour, and this is time equals t1, and let's call this contour c1. And let's say these are a bunch of fluid particles. And let's say you calculate circulation for this, integral v dot dl. Right? After some time, let's say this bunch of particles moves here and it's some other contour, right? This fluid is a deforming thing, so it won't be the same shape. So let's say it's some other shape. And these are the same fluid particles. And so Kelvin's theorem states that the circulation is the same. So Kelvin's theorem says that gamma for C1 equals gamma for C2. Okay, so if we apply this to fluid flow, to airfoil flow, so let's apply Kelvin's theorem to airfoil flow. So here you have an airfoil. Let's say it's a situation where you have an airfoil in a wind tunnel, and initially the wind tunnel is off, so there's no air flowing. And you take circulation around the airfoil. So let's say you draw a contour around the airfoil and you calculate circulation. What will it be? 0, right? There's no flow. So v dot dl will be 0 because v is 0 everywhere. So gamma equals 0. Now you turn on the wind tunnel and you get air blowing past this airfoil. Remember, it's at an angle of attack. So when you have air blowing past an airfoil at angle of attack, you're going to create lift. And if you have a lifting airfoil and you take a contour around a lifting airfoil like this and calculate circulation, what will the circulation be? Let's say it's the same contour. What will the circulation be? It will be greater than 0 because Kutajoukowski theorem says that rho v times gamma equals lift, and there is lift, and so circulation is greater than 0. So what's happening here? How come Kelvin's theorem is not being satisfied? One, here circulation is 0, here circulation is not 0, it's the same contour. It's not the same set of particles. So Kelvin's theorem says that circulation is conserved as long as you take the contour around the same set of particles. So before you started the tunnel, if you somehow tagged all the particles here with some smoke or something, and then you turn on the tunnel, these particles will blow away downstream, right? Then you can't take the same contour and say that you're enveloping the same set of particles. No, it's a different set of particles. So Kelvin's theorem is actually still satisfied, but what happens is now you really have to take the same set of particles. So initially if you had a contour like this and the set of particles was here, when you start blowing air, these set of particles will, except maybe those in the very inside of the boundary layer, except for these particles, everything will be blown downstream. So it will be like this, and maybe the particles will be somewhere here. So if you take a contour to satisfy Kelvin's theorem, you have to take a contour like this. So I'm just drawing a sketch. If you take a contour like this contour will still have circulation equal 0. So it satisfies Kelvin's theorem. Except now this contour is got blown down the back part of the contour. That's where all the particles are that were originally here. So what happens really is, if you take a contour, if you take the exact same contour, circulation is positive. So let's take this contour. That's the same as this. That circulation is positive. That means there has to be some portion which has the opposite circulation, so that this contour, this elongated contour, has 0 total vorticity. And that actually is in this, it's really a vortex of this sign. This is gamma negative. So that's called a starting vortex. So what happens is, when you have an airfoil producing lift, so this, if you have an airfoil producing lift, that would have created a starting vortex at some point whenever the lift started getting created, and that starting vortex gets blown behind, and this may be very far behind, and it looks like this, something like this. So here you have this airfoil, and this is creating lift. This got air blowing past it, and this has got a circulation of some value, let's say gamma A. So this contour is contour A. And so this circulation is gamma A. And then way behind there will be a starting vortex of strength gamma B, or yeah, so this is actually minus gamma A. So if you take a contour here, if you take a contour like this is gamma B. Gamma B is minus gamma A. So this is contour B. And so if you draw a contour that envelopes both of these, gamma A and gamma B will cancel and it will become 0 circulation strength, satisfying Kelvin's condition. So this vortex is called the starting vortex. It's called a starting vortex because it gets created when the airfoil starts producing lift. So you can think of an airplane, for example, when it's on the runway and starting to do a takeoff. At some point it will start to generate lift and it creates a starting vortex and it leaves it behind, right? Starting vortex stays where it was because we are considering the air to be stationary when you think of an airplane taking off. And so airplane leaves it behind and goes away. So over time, it's a joke. They say that they have to close down the airport because there are too many starting vortices occupying the runway. These are all silly aviation jokes that keep getting propagated, sometimes by me. Okay. So anytime there's a change in lift, there is a starting vortex. It might be a small starting vortex. Change in lift or change in bound circulation. So this circulation is called bound circulation. This, when you take circulation for a contour A that envelopes the airfoil, that's called bound circulation because it's bound to the airfoil. This contour, we always think about it as around the airfoil even if the airfoil is moving around, right? So it's bound, the bound circulation. So anytime there's a change in lift or bound circulation on the airfoil. So that happens when you start having, when an airfoil has zero lift and sometime later it has some positive lift, there's a change. It's also true when an airfoil already has lift and for some reason the lift increases. It could be due to change in angle of attack or change in some flow speed or something like that. So if you consider at time t equals t1, let's say you have an airfoil generating some lift, L1, and this is at t equals t1, alpha equals alpha 1, and free stream is, let's say free stream is horizontal for our discussion. So if you take a contour around the airfoil and calculate bound circulation, gamma equals gamma 1. So after a small time delta t, let's say the angle of attack increases. So this is an unsteady situation, so maybe the airfoil is oscillating or doing something, it's doing a pitch up maneuver or something like that. So time t equals t1 plus delta t, and let's say the alpha is increased by a small amount, so that new angle of attack is alpha 1 plus delta alpha. So instantaneously the flow will not be satisfying kata condition for a very small instant of time. So you might have flow like this. So because the angle of attack has increased, cutoff condition may be violated. We are talking about, very small instant of time. And you might have flow like this. But very quickly, because the flow is going around a sharp trailing edge, on the other side of the sharp trailing edge, it's going to have a very high adverse pressure gradient. It can't go into that adverse pressure gradient, so it will separate. And it will separate and form a vortex that is shed downstream. So what happens is this airfoil, this flow, earlier this flow was for a very tiny instant of time, it went around the sharp trailing edge, and that will form a vortex here because of separated flow. And so for a very small instant, you will have a flow like this. So you can see such pictures from experimental flow visualization in this book called Album of Fluid Motion. This is a nice, very good book with lots of flow visualization pictures, and sort of helps to understand fluid mechanics. So Milton Van Dyke put this book together. So this is what happens in that very small instant of time after the previous picture, and then sometime later this vortex is actually a vortex in the free flow, right? So it won't be staying there. It'll flow with the local velocity. Whatever is the local flow, it'll get propagated downstream. It's like if you have a stream of water flowing or something and you create a little vortex, that you can see that going away, right? It'll just get convected down. Yeah, so sometime later you will have this vortex that will be like this somewhere here, and this lift would have increased by delta L, and the circulation, previously the circulation was gamma 1. Now it will be circulation is gamma 1, gamma equals gamma 1 plus delta gamma, and this vortex is actually of strength minus delta gamma. So Kelvin's theorem is satisfied. So if you take a contour surrounding this vortex and the airfoil, the total circulation will still be gamma, which is what it was when you took this contour. Right? If you take this contour, this earlier time t equals t1, this was the gamma. But after delta t and after some time, all these particles would have moved down and they will envelope the starting vortex. And so total circulation remains conserved. So now cutoff condition is satisfied here. Is re-established for new angle of attack. And this angle now is at alpha plus delta alpha. So you get the higher lift. So angle of attack increases, lift increases, circulation increases, and there's that small shed vortex or starting vortex that convects downstream. Maybe it's better to call this shed vortex, because starting vortex is really intended to think about the vortex that's created when you start producing lift. This is more like a change in lift. So we can now connect all this to unsteady aerodynamics. There are quite a few groups in this department studying unsteady aerodynamics. Many of my students are, and Dr. Granland's lab, he has people studying unsteady aerodynamics. Anybody here from his lab? Anyway, so he's got a water tunnel that he's recently built, and one of the things he's going to do is look at airfoils and flat plates and other shapes that are oscillating and what happens to the flow around them. And these flows are very relevant in so many situations, like in helicopters, in insect flight, in wind turbines, even in aircraft, but maybe less in aircraft. So a lot of real life situations, unsteady aerodynamics plays a role. And so there's a lot of effort to understand unsteady aerodynamics. But I'll kind of try to give a glimpse of what occurs in these situations while we are talking about Kelvin's theorem and starting vortex. So these are situations where you have a pitching or a plunging airfoil. So you might have an airfoil like this that is oscillating up and down, or it's just going up, going down, something, right? It's moving, so it's unsteady. Or it might be an airfoil that is pitching about a pivot point like this. Maybe it's sinusoidally going to higher and lower angle of attack. And every time that happens, there's a small change in lift, right? When you increase angle of attack, there's a small change in lift, so there'll be a small shed vortex. But when it's going down, there's a decrease in lift. So what will happen to the shed vortex? It'll be of the opposite sign. So if an airfoil is going, sometimes pitching up, sometimes pitching down, maybe in a sinusoidal fashion, you will have alternating vortices of opposite signs. So you will have stuff like this. So something like this. You'll have this all along the wake. And this could happen, for example, for a sinusoidally oscillating airfoil. So this is a big factor. When you study unsteady airfoils, you have to take this into account. So there are theories. We're going to study thin airfoil theory. That is for steady flow. There is an extension of theory of thin airfoil theory for unsteady flow. And in unsteady flow, you'll actually have a model, an aerodynamic model that says, okay, vortices are shedding out, and they depend on the lift variation. So there's a theory that connects that. So another factor that comes into unsteady aerodynamics is something called apparent mass. apparent mass. And the way this works is, let's take an airfoil that's plunging up and down. So let's say the airfoil has a mass of m. So if it is accelerating, the force needed to move the airfoil, let's say it's accelerating this way at some time instant, let's say it's accelerating with an acceleration of a. What is the force needed to move this airfoil so that it's accelerating at this rate, at this acceleration? F equals MA, right? We know this. Equals force needed to accelerate the airfoil. Really strictly, this is only in vacuum. Because when you accelerate the airfoil and you have all these fluid particles around it, you're going to accelerate a portion of the fluid also. And so, if you, strictly speaking, in a vacuum, F equals ma. But when you have a fluid surrounding it, it depends on the density of the fluid. So when you have a fluid surrounding it, if you accelerate a body, because there is fluid surrounding it, you will accelerate a portion of the fluid also along with it. And so you can say maybe a portion of the fluid in the vicinity of the airfoil is also accelerated. So this F equals ma is only in vacuum. And so this is actually, this is without fluid apparent mass. But when you have a fluid, F is not just equal to m, but it is m plus ma times a, where ma is the apparent mass, or it takes into account the portion of the fluid that is also being accelerated because it's the vicinity of the airfoil. So this is the apparent mass of the fluid being accelerated. So this is equal to required force needed when fluid is present. So in all these situations where you have an airfoil that is plunging sinusoidally or in some other form, or pitching or something, those motions all have accelerations, and so you just can't take, the force is not just due to acceleration of the body but acceleration of the fluid, and there are ways to calculate apparent mass for different shapes of objects. And that depends on the fluid. For airplanes, normal airplanes, this won't matter a whole lot because the airplane mass is so much more than the air mass that's surrounding a small, air mass surrounding the airplane. So the apparent mass becomes small compared to the actual mass. But when you do motions in water, for example, some submarines or something like that, when they are doing accelerations or pitching or plunging, to calculate the force correctly, you have to take fluid apparent mass into consideration because water is so much denser. Even in air, I think when you come to situations where there is a lot of acceleration, like in flutter, when a wing is in flutter, that acceleration is high enough that it starts to matter that you should take the apparent mass. It starts to matter. The other situation it might matter in air is if the airplane is super light. So for extremely light airplanes like the AeroVironment Centurion, that solar powered airplane we looked at, let me see if I can pull up a picture. AeroVironment Helios, those very light, very large airplanes that, solar powered, they go to very high altitudes. The airplane mass is so small that the mass of the air surrounding it becomes comparable. And so when you talk about apparent mass, you have to take that into account. So if you take an airplane like this, so here is the solar, this is a very light airplane, extremely light, but it's large. So if you usually, this may not work all the time, but a simple way to think of how much mass of the fluid is accelerated, you draw a circle around this airfoil of diameter equal to chord. So you just basically draw a circle and all the air inside it is very close to about the amount of air that's accelerated. So if you take a circle around the chord of an airfoil like this, it's the same amount of air as in a heavier airplane with the same chord, but then the mass of the wing itself is so small that the air surrounding it starts to matter for these situations.
So do you add that apparent mass to the dynamics?
I don't know if it's that simple. So the question is, do you add that mass to the A matrix? Something like that is done. I wouldn't say exactly that's done. Okay, so I'm actually, there are lots of details and I can't even say I know exactly what is done in dynamics. But something is done, some such thing is done. It may not matter a whole lot for forward flight, but when you have to make it go normal to the flow, I think that's when it matters more. Okay, so to wrap up this unsteady aerodynamics, so here is one way by which unsteady aerodynamics might actually manifest itself in airfoil behavior. So people have known this for a long time, that if you take a CL alpha curve for an airfoil and you measure the CL at various alphas, so you take an airfoil, put it at one angle of attack, measure the CL, increase the angle of attack, measure the CL, and so on, right? So this we know. You have a linear variation and then there's a CL max and then there's stall. So this is the steady stall, steady lift curve. But if you take the same airfoil and measure the lift coefficient while it is pitching, so you don't actually let it reach steady state at every angle of attack. You just pitch at some good rate and you keep measuring the lift as it is pitching up, then you get a curve that looks like this, something like this. Okay, so it'll follow this curve, but then it won't stall. It'll actually go to a much higher angle of attack and lift coefficient before it stalls. So this is an airfoil that's pitched up rapidly. And this is unsteady CL max. Whereas this is steady CL max. And you can see this in airplanes too. If you take an airplane to stall, when you pull up abruptly, you get much higher angle of pitch, and the airplane slows down a lot more than it would if you just stall it in a very gentle condition. And one reason this happens is because of all these wake vortices or shed vortices or starting vortices. So here's the airfoil, and you're actually pitching up about this pivot point at an alpha dot, right? Angle of attack, rate of change of angle of attack. So when there is rate of change of angle of attack, there's going to be shed vortices that are of this sign. So every instant when there is an increase in lift, there's going to be a vortex of opposite circulation coming out, right? But there is a continuous increase in lift, so there's a continuous amount of shed vorticity of this sign in the wake, and this vorticity will actually cause downwash. So induced velocity induced by the wake vortices. So these are the wake vortices. Essentially these are starting vortices, but they're right now in the wake. So there's all this velocity induced, and this velocity induced will actually reduce the adverse pressure gradient. So boundary layer will stay attached for a longer angle, higher angle of attack. Right, so because stall occurs because of adverse pressure gradient. So the boundary layer can't go through the adverse pressure gradient and it separates. But when there is downwash, the boundary layer stays attached to a higher angle of attack and has higher lift, higher CL, and at some point even with this downwash, it'll have an adverse pressure gradient that becomes large enough, and the boundary layer will separate. So these are actually the sort of things my group also is, we are studying a lot of this stuff. It's pretty fascinating. Okay, so this all provides the background for thin airfoil theory, which is what the next, we're going to probably get going with that today. But let me take a short break and change the topic and talk about project 2 so that you can get started on this. So project 2 is kind of a little different from project 1. Project 1 was like a project where you have one figure of merit and the objective is to increase that figure of merit as much as possible. Project 2 is not like that. It's more of some sort of a parametric study, a design study where you design a good baseline airfoil and then change thickness and change something else and change pitching moment and do this and that and see what happens. What are the trends in cambered airfoils as you change one thing or the other? And actually a very good guide for this airfoil or for this project is this this paper I wrote long back, 2001. So low speed NLF airfoil case study. Okay, so if you should read this paper, and for the most part, project 2 is basically following that. You should see trends that are very similar to what's in the paper. Okay. So I would recommend you start with the template that I provided in Moodle, nlf1.in. You can open it in MFoil and then start modifying it. Take that template and first create a baseline airfoil. Okay, so objective is to design an airfoil for a general aviation airplane with a wing loading. This is weight to surface, weight to area. W equals airplane weight. And S equals area, planform area. So that will give you the RE times square root of CL and M times square root of CL that you have to use in Xfoil. So remember, we talked about this type 2 method of analysis in Xfoil where you don't use a constant Reynolds number, but you use RE times square root of CL and M times square root of CL. So you need this for that. And assume a chord of 1 and standard sea level. So that will give you density. The objective is first take this NLF1 airfoil and create your baseline airfoil, which will give you a maximum level flight speed of 175 miles per hour. What this means is set the lower corner of the drag bucket to this CL. Okay, so let me try to illustrate that in pictures. So your airfoil drag polar will look like this once you get it to, modify it a little bit and get it to some reasonable behavior. It'll look like this. So this is, let's call this the lower corner. So this is the CL for lower corner of the drag bucket. So remember, this thing is called a drag bucket because if you look at it like this, it's a bucket, right? Or it's sometimes called low drag range. This is the range of lift coefficients where you get low drag, and this is the lower corner, and this is the upper corner. And so if you want your airplane to go at a maximum speed of say 175 miles per hour, you want to put this so that the airfoil lower corner, the CL corresponds to at least 175 miles per hour. In fact, to be safe, you put it a little bit even lower to counteract some unknowns, let's say. Because when the airplane is going at a desired top speed, you'd like the airfoil to have low drag because it's the big contribution to drag at high speeds is profile drag. So you'd rather have drag here than here. Okay, that's the meaning of this requirement. So recall that analysis in Xfoil is done at a constant RE times square root of CL and M times square root of CL. So this is what you need to do to design your baseline airfoil. So modify the lower surface alpha star, add or subtract to all of them by a constant amount in order to set the CL for the lower corner of the drag polar to correspond to V equals 175 miles per hour. And then the airfoil I've given you already has an upper surface transition ramp. It can be improved, but it's got some initial transition ramp for it. So, try to improve it and design a similar ramp for the lower surface. So the lower surface does not have a transition ramp. So create one, add some segments and round off the corner between the favorable gradient and the adverse gradient. And then design the laminar regions on both surfaces to have laminar flow to at least 50% chord. Okay, so what this means is, this is kind of ambiguous because it is very difficult to word. The wording it's hard to put into words because the extent of laminar flow keeps changing at different conditions. But what I'm trying to say is, have the extent of favorable gradient extend to 50% chord on both the upper and lower surfaces, and make it exactly 50% so that the next sections will become easier. So that means try to do something like this. When the airfoil is in the drag bucket, you will have upper surface like this and lower surface like this, and set this to 50% chord. Let's call it 0.5 and 1. That's what we normally do. So this is upper surface, lower surface, and then you have some kind of a transition ramp, and then you have some adverse or some recovery region, something like that. Usually these will have multiple segments. Okay, so this is typical velocity distribution for airfoil when operating in the drag bucket. So that means in these range of CLs, so somewhere here, this is a drag bucket. When the airfoil is in those lift coefficients, you'll have something like this. So keep this at 0.5, set it to 0.5, have a transition ramp, and so that's the meaning of have the extent of favorable pressure gradient go to 50%. And then set the maximum thickness to 15%. Okay, so this you can set using Newton iteration. So use your Newton iteration Newt line. So let me call this 24-11. Wow, I didn't see time going by so quickly. So desired T over C max is 15%. So this will be like this Newt 1 G0 line, and use upper surface alpha stars as the Newton variable. So in other words, have your Newton iteration vary the upper surface alpha star to achieve the desired thickness. And the reason I'm saying this is because you're going to set the lower surface alpha star to achieve this, right? You're going to set this might be, let's say, CL of 0.2 or something. I don't know what it will be. But lower surface alpha star you set to achieve this, then that means you shouldn't change it. Don't use that as the knob for thickness. Use the upper surface alpha star as the knob for thickness. That's how it's done in the paper too. So do that. And then, yeah, plot the velocity or CP distributions for the airfoil for a range of angles of attack. Some of this is, I'm really not giving very step-by-step instructions. By this point, you have to start being able to think of what is important to show and what is not. So I'm just going to say, for a range of angles of attack, show me velocity distributions. You think through it and say what is important and show that. Don't just plot for 100 angles of attack all in one plot. It'll be like one big blob. Okay, think through it nicely. Plot the polar for the appropriate RE times square root of CL. Discuss briefly how the airfoil meets all these requirements. Part B is take this airfoil, vary the thickness from 12% to 18%, maybe like 2 airfoils below and 2 airfoils above, something like that. Keeping the extent of laminar flow the same, discuss the results. This is actually follows pretty much what's there in the paper. Third part is, now take the baseline airfoil. So from here you go to the baseline to B and then baseline to C, right? From the baseline airfoil with the thickness kept constant, now vary laminar extents. Instead of 50%, make it 30%, 70%, and see what happens. So use that Newt1 I think S0 line to set x over c of segment endpoints. So if you want to set a segment endpoint to 50% chord, there is a Newton line for that, and I've talked about it when we talked about M-foil. So when you do such things, do it one at a time. Let's say you want to set several segments, each one to a different x over c for some reason, okay? There's no one way to do this. Just don't start putting all the Newton lines together and run it, because it's like writing code. Do one little thing, there'll probably be some error, debug it, make it work, and then you'll say, oh, I know how to do this, and then do the other one, then do the other one. So add things progressively. Don't make it all complicated without running it and then try to run it. You won't know what's going on. And then the last part is nothing to do with profile at all. Take the baseline airfoil, deflect a 15% chord trailing edge flap, 5 degrees, 10 degrees, up and down, and see what happens to the drag bucket. Okay, so let's stop with that. We can talk some more if you have questions on the project. Okay, thanks.